Welcome to this video on ionisation, part of the radiation topic for National 5 Physics. So the things we'll be learning about in this video include what is ionisation. That's what is, when it says what is meant by the term, it means what is ionisation, and the difference between the amount of ionisation that alpha, beta and gamma do, and the effect ionising radiation has on living and non-living tissue. Here's a diagram of an atom, and this is the atom of carbon, and carbon is atomic number 6, and that means it has 6 protons in the nucleus and 6 orbiting electrons. You may have learnt that from chemistry. What we're interested in physics is not particularly the number of protons and neutrons and electrons, but that there are the same number of protons in the nucleus, the center of the atom, shown red here, as electrons blue that are around the nucleus of the atom. So as we were saying there, atoms usually have the same number of protons, which are the positive charges, and electrons, the negative charges. So that means that the atom has no charge overall. So in the case of carbon, there are 6 protons, each having a charge of +1, and 6 electrons, each having a charge of -1. So 6 plus -6 makes 0. Ionisation is the addition or removal of an electron from an atom. So here's an animation of the same thing. So the protons in the nucleus, which are positive, and there's electrons which are negative, which are orbiting around them. Normally there are equal numbers of protons and neutrons, so it is neutral. If we add an electron, then instead of having just 6, we've now got 7. So the overall charge is -1 because we have 6 pluses, but -7 for the negatives. So we form what we call a negative ion. If we remove an electron, we now have the 6 protons, but only 5 electrons. So we end up with a positive +1 charge on our ion. So here's our atom here with the electrons orbiting around. We freezed it there to see that there are 6, and then now ionisation has happened because we've now only got 5 when we stop. So it's now an ion because we've lost an electron, and that can happen because of alpha, beta or gamma radiation. So now we've got back to 6, and this time instead of removing an electron, we're adding an electron, which is what can happen with nuclear radiation. And so we get 7 electrons instead of 6, so we've got an ion, and that's ionisation. So ionisation is the addition or removal of an electron from a neutral atom to produce a charged particle. Here's an animation kind of showing what it's like. Remember, these are really small. Even the alpha particles, that the largest, 2 protons, 2 neutrons, are very small and we can't actually see them. So imagine the alpha particle passes the neutral atom, and what it does is it takes away an electron. So we are left with an ion. Remember, we've got our 3 types, alpha, beta and gamma. Alpha is the most ionizing. 2 protons, 2 neutrons make it up, and because protons have positive charge and neutrons have no charge, it has an overall charge of +2. Alpha is the most ionizing type of radiation. But even though it's most ionizing, it doesn't actually penetrate the materials very much. Okay, sometimes larger atoms release alpha particles to become more stable. That's what the radioactive sources are. Alpha particles can do a lot of damage to human cells, but they need to get there. They would not go through the skin of your body, but if you ate or breathed in alpha particles, then they're right next to your cells and they can harm them and cause cancers, and people have died because they've eaten some radioactive alpha particles, alpha materials that emit alpha radiation. Beta is our fast-moving electron from the nucleus. It has a negative charge, it's very small, it's less ionizing than alpha, but more ionizing than gamma. And it's coming from the nucleus, and the neutron changes into a proton and emits this electron, this beta particle that's there. Gamma is a high-frequency electromagnetic wave, travels at the speed of light, 300 million meters per second. It has no mass and no charge. It penetrates lots of things, but it doesn't do very much ionization. So gamma will travel through your body, but it does less harm than alpha does because it doesn't do as much ionizing. It does still do some harm if the dose is high enough though. And gamma radiation is used for radiotherapy, where nuclear radiation is used to kill off living cells, kill off those cancerous cells. So gamma has the most energy, it's the most penetrating, it's the most difficult to stop. Remember, it will pass through paper and aluminium and can only be stopped by a few centimeters of lead. So all types of nuclear radiation can sometimes be called ionizing radiations because that's what they do. They ionize the living cells. They kill or they change them. If they kill the cells, that's obviously a problem. If they change the DNA and the structure of the cells, then that can cause cancers, and that makes them potentially dangerous. We can think about them in terms of ionizing density. You really just need to know which one's the most and which one's the least. You can see them in a ionization chamber. So here's an alpha source in that. You can see these trails that come because there's lots of ionization occurring in the cloud chamber. Beta, much less, thinner trails, less ionization. When we switch to gamma, you won't see the trails at all because the gamma source really doesn't do any ionization at all. So you need to know what ionization is, but also that alpha particles cause the most ionization, beta less, and gamma the least. So there's an alpha particle ionizing the air as it goes through, creating positive and negative charges, adding or removing electrons. Here's our beta particle doing a bit less ionization. Here's our gamma radiation moving faster, doing less. Each time a particle causes ionization, it loses energy as it's absorbed. Alphas does a lot of ionization, so it doesn't go very far in air and it's easily absorbed. There's a lot of ionization of paper, and that's why it doesn't go through paper. Beta does less ionization. That means it travels for longer in air than alpha. Gamma does the least, so they travel the furthest. One of the other ways of seeing ionization of individual atoms is in a spark chain counter.
Next, we're looking at counting the individual alpha particles.
I'm going to connect the negative side of the high voltage power supply to the grill on the top of the spark counter. Underneath the grill, you'll see there's a thin wire which I'm going to connect to the positive side of the power supply.
Teachers sometimes find spark counters don't work very well. The main cause of problems seems to be dust. We recommend the spark counters are kept in plastic bags to avoid build-up of dust.
As I increase the voltage, in the end I will get a spark between the mesh at the top and the wire underneath. If I reduce the voltage down from that though, I want the point where it's just stopped sparking. When I introduce the radioactive source, which is producing alpha particles, when one of those alpha particles fires through the gap between the mesh and the wire, it causes a spark. That's because each alpha particle, as it passes through, is causing ionisation, allowing a spark to happen between the grill and the wire. We can see the mesh across the top, which is connected to the negative side of the power supply, and the wire underneath, which is connected to the high voltage positive side. As the ionising radiation comes in, it causes the sparks to happen. As we zoom in, an alpha particle is coming from above, and it ionises one of the air particles between the gap. That's then accelerated upwards, and that causes a cascade of ions hitting each other, which we see as a spark. Each ionisation particle coming in is going to cause a spark of its own.
Next, we're looking at counting.
Okay, so what we need to know is what is meant by the term ionisation and the different levels of ionisation for alpha, beta and gamma.